Okay, good morning, everyone. So my talk will describe the development of a calculus system to derive air pollutant emission from real-time traffic data. This work was done by two companies, UHOP and CHISMA. The first one more on the informatic part, and the second one more on the conceptual part. Okay, first thing, why monitoring traffic emissions? First, well, traffic and then emissions. We have two issues. The first one is a local one. We need to know air quality data because pollutants are an issue for health of people. So we name this one on the left local pollutants, for example, nitrogen dioxide, PM10, carbon monoxide. On the other hand, we have a global issue, and this is related to greenhouse gases emissions. Okay. All the system was based on two main components. The first one is called the pollution connector, which takes all the traffic data which already are in the open data system and then pushes back the results as a value-add information back to the open data, so they can be then they are available to data consumers. The other component is the so-called emission model, which does all the calculation to derive an accurate estimate of emission based on real traffic data. On the informatic part, so the pollution connector can be schematized, has this schema. So we have at a higher level scheduler, which creates periodic tasks to update the pollution data. And then we have a pollution computational task handling all the computation, so getting batches of real traffic data and pushing back the results. And we have a pollution computational model, which is called each time new fresh data can be pulled from the Open Data Hub. The pollution connector, a bit more in detail, has this schema. So the scheduler starts the execution each 10 minutes, so we have really fresh data. It downloads the list of available traffic sensor stations and checking if they're working and if they are online and delivering the traffic data. Also downloads the last pollution data which were calculated at the step before in order to check if there is some overlap or something or some problems like that. And then identifies a new traffic to be connected. All these checks are useful in order to identify a problem as we are working really in real-time operation. And then the pollution computational model computes new pollution information for all the gases we described before, so NOx, PM10, PM2.5, and CO2, which is the greenhouse gases, which is very important at this time. And finally, the main task uploads the new pollution method to Open Data Hub back. Moving to the emission model. So conceptually, we need two data sets. The first one has to be real time, and this is built up by transits. So how many vehicles are flowing at a traffic station, and this is the integral over 10 minutes, and then we also need the speed of the vehicles at 10 minutes average. Then there is a second data set, which is called a semi-static data set, namely road geometry, which is not going to change very often. Then we have the fleet composition, which is typically based on statistical data. Fleet composition means how many light vehicle and heavy-duty vehicles we have, which aero classes are flowing on the street, fuel type, and so on. And this is typically updated once a year and can be done based on national inventories of fleet composition. So all this data are put inside an algorithm which is based on a European standard, which is named COPERT. COPERT means computer program to calculate emission from road traffic. And COPERT is both a software, a standalone software, we didn't use this, and is a methodology which is open and declared, and so you can recreate it, and we use this in order to have a real-time model, while the original software, we can say, is only used for planning and for statistical analysis in an offline mode. The output of all this is emission data, which is given in grams per kilometer driven for all these gases, and depends on subdivision of vehicle in type according to fleet composition. It depends on Euro classes and fuel time, and this is put inside these coefficients. So for each vehicle class, we have a formulation like the. We have a formulation like this, where V is the driving speed, emission factor is the specific emission of each pollutant in grams per kilometer for each vehicle, and all these coefficients depends on pollutant, vehicle class, fuel type, and Euro classes, and so on. And that's why we have to update them at least once a year, because fleet composition is changing in time. The first case study and the first deployment was done on A22 highway. And why A22? First of all, because as Ilaria De Biasi told before, they are going towards a digital infrastructure, so we do have many data available and also high quality data available. And the second motivation is that this highway is the most important traffic axle crossing the Alps, so I would say this is a very important and significant case study to understand how pollutant emissions are varying in time and space. So in space across the highway stretch, and in time looking at weekly pattern, yearly pattern, and also daily patterns. Here we have some examples which are extracted from Open Data Analytics. As I told before, traffic data are already on the Open Data Hub. We get them, we calculate pollutant emission, and we pull back them so they can be described and visualized in the same way traffic data are already done. Some example. So here we have the CO2 emission by vehicle category along A22. This is an example of April 2023, and this is all the stretch from Brno on the link to Modena. And why are we seeing some variation in its total CO2 emission, because in each stretch we have different speed, different fleet composition, different total flow. So from one stretch to other, total flow is changing, obviously, and also all the other characteristics. So we have to look at these features, and we can, in this way, derive how emissions are varying in space, and also how they are varying in time. This is another example. At a given traffic station, this is the case of Bolzano, we can have a weekly pattern of emission, and in this case, we see very clearly the minimum of CO2 emission in the weekend, where heavy-duty vehicles are not circulating, and so the blue line has its minimum, and on the other hand, we see the patterns, the weekly patterns of light vehicles, which are very different features. Back to some informatic issues. So the access data is done through API to the Open Data Hub, and they are very similar to the API in the mobility domain. So in the same way you get traffic data, you also get emission data, and this can be done directly to analytics, or also through libraries, for example, written in R, which can help accessing all the database. What about the context? Can we scale and replicate this? Yes, we can, but with one warning. Obviously, we need traffic station. If we want to replicate this in another street network or on another highway, we obviously need a traffic station, and they typically are already on site. The only problem is that data are typically closed, or they are stored but not shared. And the second issue, which is indeed not a real problem for applicability and scalability, is that we have to redo and recalculate in a statistical way the fleet composition for every region we would like to applicate this method again. But this can be done on a statistical basis, as I told before, and is quite standard. What's next? What can we do with all this emission data? Some example which seems quite important to me. First of all, estimate carbon footprint on the whole road axis or on a network, if we are talking about an urban street system. Then also assess the pollutants or carbon reduction over here. This is important because we need to create indicators in order to understand if policies are running well, or if they are, or if they have to be modified. And last example, get input for air quality modeling, which are in a future could be a useful tool in order to do good planning for traffic management. And that's all.